Disregard the algorithm.
Ô record à?
Thầy nhớ cậu bao nhiêu mà cậu quay sáng tối rồi?
Gì cơ?
Cái thầy nhớ này nó bao nhiêu mà cậu quay?
Nó quay được 2 tiếng liên tục.
Thầy nhớ của cậu mấy ghi?
32 ghi.
Đầy ông quay một lần gì một tiết học gì đầy
Quay
luôn không?
quay 1 tiếng thì nó được khoảng nó mất tầm 7 ghi.
我想约要派一起上个6单位。
Này nó có support đến 64 ghi không? Thầy nhớ nó có nhận.
Nó có loại 64 ghi.
Mình nó có nhận không? Phone nó có nhận không?
Nhận nhưng mà tớ cần 32 ghi rồi.
Nhiều quá nó hư rồi.
Không cần đến 64 ghi. Ảnh ấy thì sau một thời gian tớ copy hết ra máy.
Tại vì cái giá nó cũng rẻ, 64 ghi không mấy đồng như nhiêu không? 12, 13 đồng, 15 đồng.
Ồ thế à?
Để xe á. Giờ thầy nhớ rẻ.
Ồ thế thì hôm nào mình ra xem.
Giờ thầy nhớ rẻ om mà. Nhưng mà mua cái loại 10x, mua cái loại 10x thì nó nhanh hơn. Đừng mua loại 2x. 2x tổ chậm.
I don't remember that I have to give any announcement, so sorry. If you have questions. Any questions before I start? All right. So, okay, so here's one, I guess this is an announcement. So, as far as material in this section, it has to do with linear programming. So,
Anh đang tìm giáo trình ở đấy.
okay, so this is a very big subject, and there are whole books written on linear programming. And so I don't want you to read all those books. I just want, in fact, I think we'll be done with what we need to see by Monday, maybe, for sure by Monday, but maybe even Friday. I just want to get some basic ideas across. But as far as reference, everything that you'll need for this class is discussed in chapter 29 of the famous book by Corman, Vertices, and Vertices. And you can look there, and it's got all the things I'm going to. Well, the examples might be different, maybe bigger, but a lot of the stuff is there. Okay. So I just want to get a few ideas across here. We're not going to become experts on linear programming. There's tons of stuff to learn, and in fact, after we're done with this part, we'll probably see a sprinkling of other things later about linear programming. But it's not really the core. It's just that it's not like the central topic of this course, but in some sense it is, because it's kind of the limit between what's solvable efficiently and what's not, at least in theory. Okay, so here's my diagram from last time of simplex. So the simplex is an algorithm for linear programming. I'll tell you right off the bat, simplex is kind of like Ford Fulkerson in the sense, or actually Ford Fulkerson is kind of like, is in some sense a version of simplex. And so right off the bat I'll tell you that simplex is not, at least there's at present no known version of simplex that runs in polynomial time. But in most cases simplex does very well. And there's some mathematical reasons for that, but some aspects of it are still not fully understood. So simplex is not known to be polynomial, but one of the main facts that we will need later is that, in fact, even though simplex is not, the problem can be solved in polynomial time. Okay, so there's this basic fact that linear programming can be solved in polynomial time, but maybe not through simplex, although still some questions about that. But there is that. And it's kind of nice to understand what the underlying geometry is, because from time to time we'll need to invoke it. Okay, so anyway, so I'm going to talk about simplex and tell you, first of all, So here's an example. This is a sketch of what, a cartoon of what simplex does. It starts at some feasible solution, and that feasible solution is going to be always a vertex of the feasible region. And from there it's going to move and move and move from one feasible solution to another, from one vertex of the feasible region to another vertex of the feasible region, as long as there is improvement. Okay, so this move from vertex to vertex is what will be called a pivot. Okay, so this is called pivoting. So in fact, pivoting is a lot like finding an augmenting path. In fact, if you think about it sort of geometrically and translate the geometry into graphs, and you just stretch your imagination a lot, okay, you will see that there is an analogy. So there's an analogy between pivoting and augmenting paths. All right, and in fact, if there is a point at which you keep pivoting and pivoting, and if you get to a point like this one, assuming that the maximization is in this direction, if you get to a point, a vertex where all the neighbors have lower objective value, then there is no more pivoting, no more pivot that's going to give you an improvement, so at that point you can stop. So you declare this one to be optimal. All right, so it's when you stop because you can't pivot, it's kind of like when you stop in Ford Fulkerson because there's no augmenting path. All right, so there's this kind of analogy too. You have no pivots, meaning no augmenting paths. Furthermore, in flows, we know that when you can't find an augmenting path, there's in fact a cut whose capacity matches the current flow. All right, so a cut in a graph is sort of edges that are basically the capacity of a cut is limited by the capacity of the edges that go across it. So it's in some sense, it's a linear combination of the capacities of those edges. That gives you a bound on how much flow you can send. Well, for linear programming, there's a similar thing in that you can get bounds on the optimum solution based on the constraints. I showed you an example the other day. I'm going to maybe show you an example, maybe not today, maybe Friday. So there's a sort of parallel dual problem in which you're trying to minimize some objective function, and everything kind of depends on the constraints. So when this dual problem is minimized, you've actually achieved a maximum and a primal, and there's a kind of connection there between those two, which is similar to what happens between flows and cuts. So with that, let's look at that for later. The other thing I noted last time was that it's possible that you have a situation like this where the problem is unbounded, so you try to maximize in that direction, for instance, and the feasible region, it goes out to infinity, and there is going to be there will never be an optimum, or a finite optimum in this case. In fact, if you had been maximizing in the opposite direction, like this way, there would have been an optimum. So I think it would have been maybe this vertex. All right, so even if the feasible region is unbounded, it's quite possible that you have a bounded feasible solution or an optimum solution, but it depends on the direction in which you're trying to maximize or minimize. All right, so that was the thing. Now, the other thing, so here's the sort of form linear program we're going to study here. The linear programs we're going to study here all look like this. We're maximizing a linear function subject to constraints that look like this, less than or equal to constraints, and non-negativity constraints on the variable. So that is what we call standard form. And what I argued last time, and some people had questions after class, but I think about them, they're not too hard to answer, but you can always convert any linear program into one in standard form by maybe adding some constraints, redefining some or adding new variables, but you can do that always and get to this. And the transformation from an arbitrary linear program to a linear program in standard form is a polynomial transformation, meaning you don't blow up the size of the problem exponentially. Keep it, it's bounded, the size of the new problem is bounded polynomially in the size of the original problem. So this is standard form. One more thing. So what about the vertices of the feasible region? what can I say about them? How are they defined? Well, so in terms of this, okay, so in terms of these things, what do they correspond to? So each of these constraints that we see here is a half space, and so we have a bunch of half spaces, and their boundaries are hyperplanes. Okay, so you've got this like the hyperplane. Depends on the dimension, but you know, in 3D it would look like this, and then you have this side and the other side, and each of these vertices corresponds to the, like 3 dimensions would correspond to the intersection of how many of these hyperplanes, or half planes. 2 would give you a line, right? And then a third one would give you a vertex. So in general, each of these vertices here corresponds to a set of constraints, and so when we are pivoting, we're effectively going from, let's say, one set of constraints that define a vertex to another set of constraints that define the next vertex. Okay, so it's kind of like you're going from one, which we'll call basis, that's what we'll call it, to another basis, to some set of constraints that define a vertex to another set of constraints that defines another vertex, that's a neighbor. All right, so that was what I said. Then there was one more thing, and this I said very quickly, so let me review that. So here's a variation on standard form, and this is the form we're going to use for solving our linear programs using simplex. This is called slack form. So in slack form, what we will do is we will introduce variables for each of these constraints, each of these this first set of constraints. Okay, so this constraint, this extra variable, will correspond to the difference between the left-hand side and the right-hand side. And so we're going to write it like this. So slack form is do it higher. Z equal to this will look like the same. Okay, so this is just the original objective function, except that I'm just going to call it Z. And then I have these additional variables and new constraints. All right, so I'm going to add, this should be a plus, not a minus. Okay, so I'm going to add a bunch of constraints, or actually add a bunch of variables, one for each of these constraints, so it's going to look like this. So bi minus this side, so bi minus aij, xj, so this goes from j equals 1 to n, this goes from j equals 1 to n, and this is from I equals 1 m, and all these variables here are going to be non-negative. All of these are assumed to be non-negative, so I'm going to write this in parentheses indicating that I'm making that implicit assumption. All right, so let's see. So I've added m variables, one for each of those constraints, and just kind of flip things around. So now you can see here visually that each of those new variables corresponds to the difference between the b and the sum of those BIX. All right, so if you maybe one way to think about it, it's not really precise, but one way to think about it is kind of tells you how far away you are from the boundary of a half plane of a constraint. Not really that, but it's kind of some indication of that. All right, so again, this transformation only adds what is it, m variables, and so it's still going to keep you within some polynomial bound of the original problem. So it's not really making things enormously larger, but it does make things easier to manipulate, as we'll see in a moment. Okay, so let's do an example, because maybe it's easier to start with a concrete thing and then go to something more general. Okay, so here's the example. I'm going to maximize, let's say, 2x1 plus 2 subject to, and here are the constraints, 2x1 minus x2 x1 equals 2x2, and all of these should be less than or equal to constraints. All right, so here are the constraints, and I'm assuming that this is a standard form, so I have x1 and x2 bigger than or equal to 0. Okay, so this is the original problem I'm trying to solve, and this is the original. All right, and now let's write it in Slack form, and I'm going to just use the standard way of writing it. All right, so I'm going to do it. It's going to look a little bit strange, maybe initially. So I'm going to put here a 0. Okay, so that 0 is in effect the objective value for our initial feasible solution, which I will tell you right away is going to be x1 equal to x2 equal to 0. Okay, that happens to work. Okay, so at x1, x2 equal to 0, I have a 0 objective value. But that's going to change as I pivot, as I move from one feasible solution to another. Okay, so that's just the objective function. And then I have the slack variables. There are the slack variables x3, x4, x5. So x3 is going to correspond to the first constraint, so it's going to be 4 minus all this stuff. Right, so it's going to be 4 minus, what is it? 2x1 plus x2. Thank you. 2x1 plus x2. And the next one is going to be 9 minus 1 minus 2x2. And the last one is 3 plus x1 minus x2. Let's see if I got this right. I think I did. Okay, so this is the slack form. So I'm assuming here, I'm not writing it, but I'm assuming that everything is non-negative. x1, x2, x3, x4, x5 are all bigger than or equal to 0. All right, so this is the slack form of this. And as it happens, in this case, x1, x2 equal to 0 is feasible. Is that correct? Is x1, x2 feasible? X1, x2 equal to 0 feasible? Yes. Yeah, of course, because it's you get zeros on all of these what's it, the left-hand side, and they're all less than or equal to 4, 9, 3. So that's really okay, and so it's all feasible. Okay, so x1, x2 equal to 0 is feasible, and you can see that because in this two-dimensional linear program, the origin x1, x2 is indeed a vertex of the feasible region. If you drew it, you'd see that. All right. So here we are. We have a slack form problem, and here's what you can see. And this is why we write it like this. Okay, so let me maybe write it here. Okay, so let's say that x1 equal to 0, x2 equal to 0 is feasible. All right, now, if x1 and x2 are 0, what is the value of x3? 4, and the value of x4 is 9, and the value of x5 is 3. Okay, so it's feasible, and in fact, this automatically tells you that x3 equal to 4, x4 equal to 9, and x5 equal to 3 for those particular for those choices of x1 and x2. Okay, so the first observation is that given that these things here are 0, the variables on the right-hand side is 0, you can read off first of all the values of the slack variables, or these variables on the left-hand side. You can read them off directly, just read these off. But furthermore, you also know the value of the objective function, which is this, right? It's 0. Right, so everything that you need to know about this feasible solution is visible here in this particular format. Now, I don't know why it's called this way, but because perhaps you can see everything that you need to see, this is sometimes called a dictionary. I don't know who invented that term. So it's a dictionary. You can sort of read off what the variables are and the value of the objective function is directly from this particular layout of the problem. All right, so that's kind of nice. So I've started. So if I look at this, I have. I mean, if this were x1 and this is x2, I don't know what my feasible region looks like. Maybe it looks like this, but I'm right now here at the corner, and I now need to move to a better solution, right? So I'm trying to maximize in the 2, 5 direction. All right, any questions so far? Yes, this is where we're starting. So I really haven't done anything. Now, if I look at this, this is the other end of this particular layout, is I can see that x1 and x2 have positive coefficients, right? So this is 2, this is plus 5, which means that if I increase either x1 or x2, I will increase the value of the objective function. That means if I go this way or that way, the objective function will increase. And I will increase, I guess, there's probably going to be a limit on how much I can increase, because if I increase too much, I'll eventually hit a vertex. Okay, maybe this way or this way. All right, so I have to figure out how much I can increase. I can't increase arbitrarily. That's determined by the constraint. If I can see either one of these will give me an improvement. If I increase x2, I'll go up by 5 per unit of increase, whereas here I'll go up by 2 per unit of increase. So let's just be greedy and choose x2. Okay, so I choose to increase x2. All right, so now I look at these constraints, and okay, so for instance, okay, so I'm going to increase x2 while keeping x1 at 0. So I will move up this way. That's what I mean, right? Just keep x1 at 0, so I'm moving that way, and therefore I have a bunch of inequalities. For instance, here I have this is 0, so it says that x3 equal to 4 plus x2, but I know that x3 has to be bigger than or equal to 0. Okay. No question? Okay. So let's just do it. So, okay, so for instance, let's look at this. Let's look at this first one here. Okay, so this one, I know that x3 is bigger than 0, and I want to keep x1 at 0. So I know that I must have x2 plus 4 bigger than or equal to 0. Right, because this x2 is this. Okay, so I know that because that just expressed the fact that x3 is bigger than or equal to 0. So this says that x2 is bigger than or equal to -4. Okay, what does that say? If it doesn't say anything, tell me so. It doesn't say much, right? It says, okay, x2 has to be something bigger than -4, but that's all right because it's going to be. So this doesn't really put any constraints on x2. Okay, so this just says it's bounded from below, but I really don't need to worry about it. Okay, how about the second one? Okay, this one says that -2x2 plus 9 is bigger than or equal to 0. Right, so -x2, so that says that x2 less than or equal to what? 4.5, right? So, okay, that does tell me. Okay, it says I cannot go above 4.5 in this direction, for sure. Okay, so that's for sure. And what about this last one? Well, this last one says that x2, can you tell me right away what it says? Less than or equal to 3. Okay, so I have 3 constraints defined by these 3 constraints. 3 constraints on how much I can increment x2. So I can either, so I have the first one which says no constraint, the other one says at most 4.5, and the other one says at most 3. And the tightest of these constraints is, of course, the last one. Yes, go ahead.
I'm not sure how we're coming up with the constraints that are circled there with the variables inside the box. Like up above we have constraints, but those are.
Yeah. Okay. So each of these is bigger than or equal to 0. So I have to maintain that each of these remains bigger than or equal to 0. I have not written those additional constraints here, but I could have written that x3, x4, x5, as well as x1 and x2 have to be non-negative. So these all have to be bigger than or equal to 0. Right, so that means that I will not violate the original inequality. Right, for instance, the fact that this is bigger than or equal to 0 means that 2x1 minus x2 is less than or equal to 4. Yes?
The x2 less or equal to 3, I think, is actually not very tighter than the second one, because like in x5 you have x1 greater than 0. So that means you can increase it. So when you increase it, you can have x2 not as tight as
Well, I mean, so I'm keeping x1 at 0.
But that is something not constrained.
No, you're not constrained. Of course, you're not constrained. But well, okay, we're not constrained by the linear program, but we are constrained by the approach I'm taking. So the approach I'm taking is I'm moving from vertex to vertex. Okay, so I'm keeping the sort of x1 equal to 0 constraint kind of tight, but I'm just moving in one direction. Okay, so yeah, I mean, in fact, I guess maybe that's what led people to better linear programming algorithms, because they figured, I mean, I don't have to be constrained to moving from one vertex to another in the feasible region. Maybe I could go this way and get a better improvement. Actually, that's true. There are ways in which you can go inside and do better. But in simplex, we're just going along the boundaries. Yes?
We can have this result from the orthogonal constraints, so why don't we need the flash probe?
Sorry, why do we need what?
The result, we can get this from the orthogonal constraints.
Uh-huh.
So why don't we need the slash form?
Which one? These?
Yes.
These, why do you need these instead of just this?
Because from this I can get this result also.
Yeah, sure.
So why do we need this one?
Okay, 2 reasons. One reason is it actually makes it easier to describe the algorithm. Okay, so that's kind of cute, and I will see. Second reason is that these variables, these weird variables here, will eventually, as you'll see in a moment, wind up in the objective function. When they're in the objective function, they'll have some coefficients, and those coefficients will be essentially the solutions to the dual problem. Those coefficients will be the proof that the solution is optimal. Okay, how does that work? It's linear, the magic of linear algebra. Okay, but yes, so it first of all makes it easier to write this, all of this, explain the algorithm, but it actually gives us a proof as well. Just, I don't know why it works that way. No, I kind of sort of know why, but it's... Any other questions? Yeah, so I guess the whole point is, you know, when you first see this, okay, why did I go from this to this? Why do I need a slack form and all that stuff? It organizes things better. It's easier to write algorithms, but it also gives you proofs. Okay, questions? Other questions? Yes, 2 questions, yes.
We start with a 0 for z.
Yeah.
So now let's say the maximize function has a has another constant, let's say +3. That means we'd start with 3, right?
Yeah, but you wouldn't need the other. I mean, if it has another constant, you don't need to worry about it, right? I mean, I guess if you have a constant, if you have an objective function, you can just throw it out because you can add it up at the end, so that's not a problem. But yeah, I guess as you'll see in a moment, we will have some other constant here, and that will start building up. Yeah, somebody raised a hand. Yes.
Yeah, in the slack functions, when you write like, so we assume all x1, x2, x3 should always be greater than 0, is it?
Yeah.
So if we have a constraint in the original problem, like for example, x1 plus x3 is greater than instead of the less than.
No, okay, no, then you have a problem. You can't. Okay, so if you have strictly greater than constraints, it's actually not. All of this is not quite right? Because if you have strictly less than, how can you actually optimize? Okay, it's just think about it. Yeah. So that's a good question. What about less than constraints? Well,
Can you just like solve the problem in terms of like less than or equal to?
Yeah.
Say that the answer is the limit to that vertex.
Kind of the limit, yeah. But then you start talking about limits and stuff. Yeah. Yeah. Then you're out of the realm of discrete math. Okay, so I'm okay with being outside that realm actually, but here we're in the realm of discrete math. Just the way it is. Other questions? Yeah, so yeah, you did get to the limit, right? You can't get you can get kind of close, arbitrarily close, but not quite there. All right, other questions? Okay, so anyway, so we know that of these constraints, if we're going to stick to this moving along the boundary of the feasible region of these constraints, the tightest one is this one. It says x2 has to be less than or equal to 3. Okay, so I increase x2 up to, I will increase x2 up to 3. What will the value of the objective function become? 15, right? So this will go from 0 to 15 in one jump by just going straight to that vertex. All right, so I know that. Any questions why that's true? Right? So I just go up to 3, that's by 3, then 3 times 5 is going to be 15. So now what I want to do, though, is such a way that I get a dictionary for this new value of x2. Okay? So here's the structure I'm after. So here, let's do that. Okay, so I have this form, and okay, so I have this thing called a dictionary, and the dictionary which you see there will always have this form. We're going to have form b prime, which is the constant, and this initially is 0, and then plus okay, so here I have some xj, some cj primes. Okay, and I have defined this set n, capital N. Okay, so capital N stands for non-basic, and we'll have a set capital B which will stand for basic. All right, so these are the basic variables of our problem, our current problem. So these correspond, in fact, to the vertex we're at currently. So initially, we have x1 and x2 because it's those two variables, the intersection of x1 equal to 0 and x2 equal to 0, that corner, that's what defines the initial feasible region. But it's going to change, or the initial feasible solution. But that's going to change as we move from one feasible solution to another. Okay, so this is going to be C J prime because it's not the same as the original CJ. It's going to be different. And then on the other hand, we're going to have a bunch of constraints that look like this. Xi equal to B J Bi prime minus some Aij prime. Again, these are not the same as the original ones, xj for j in n. And this is for all I in the set B, which is the set of basic variables. All right, so that's what a dictionary, that's the sort of shape I'm looking for. But I also want one other thing. And this is really important. So for each non-basic variable, I want that xj is equal to 0. Okay, so for all of these guys on this side, like in this example, x1 and x2 were both 0. Okay, so that because they are non-basic. And now the basic variables, which are these guys on the left-hand side, are just going to be equal to these b's. Okay, and so for each j in the set capital B, xj is going to equal bi, actually xi is going to equal bi prime. So I should have I in B, and this should be I in bi prime. I equal to bi. Okay, so the reason I'm doing this may, when I do it like that, it seems very abstract, but you'll see what it means when I do it on this example. So what this means is that because these are zeros, I have that the objective function value is going to be this z prime, right? So this is going to, or this v prime right here is going to be the objective function value. And then I can just read off the values of the basic variables very easily from the dictionary by just looking at these numbers. Okay, so let's just see what happens. So I know this is the tightest constraint, right? This one says x2 is less than or equal to 3. So what I will do is I will increase x2 up to 3. Right? So that you saw increasing the objective function to 15. When I do that, what does the value of x5 become? What is x5 when I make x2 equal to 3? 0. All right, so I will, when I increase x2 to 3, x5 drops to 0. So what I will do is I will make x2 a basic variable, and I will make x5 a non-basic variable because it's now at 0. Okay, so it's like x2 and x5 will swap roles, and so I'll have like x2 equal to 3 plus x1 minus x5, and then I'll express everything in terms of x5 here. Okay, so I just kind of do this, or x1 and x5, I just do some algebra. So let's just do it. All right, so here's my first dictionary. So my second dictionary is going to look like this. Z equal to 15. This is the value of the objective function. Okay, so now I have that x2 is equal to, what is it? x5. Okay, so if I do the algebra, it's going to give me this. So 7x1 minus 5x5. Okay, so what I did is I just solved for x2 here. Okay, so I got, I don't know, let's say, okay, let's put this on the corner here. So what I did is I made that, I said x2 is equal to 3 plus x1 minus x5, and I just kind of substituted in there. So I just multiplied this by 5 and did the algebra, and I got this. Okay, so I get this new value, and so you can see the objective function is value is there, and then x3, x4, and now x2 instead of x5. All right, so you know what x2 is going to be 3 plus x1 minus x5. Right, I just copied what I did here, and then I just substitute this in each of these two equations, and I get something new, which is going to be, I'll write it down, 7 minus x1 minus x5, and 3 minus 3x1 minus 2x5. Okay, so this is a pivot. So I moved from dictionary 1 to, if I'm wrong, just correct me. I think I'm correct if I did the algebra right. 7x1, yeah. So I just a substitute. I moved from one dictionary to another, and you can see here, okay.
Your x4 it should be like minus plus 2x2.
For x4 it should be plus.
Plus 2x.
Should be plus 2x5?
Yeah.
Are you absolutely sure of that?
Yes.
Yes.
100%?
Yep.
Yes.
Everybody's 100% sure of that. Okay, so it's minus 2x5. You could be quite right. So it's so you think, so what you're saying that this is plus this one here? Okay, let's keep it there. I don't know, maybe you're right. I guess you're right. Okay, so and if you're wrong, you can correct it. I mean, you can check it. But okay, so what can you see here though? Regardless of that. So you know that first of all, for the second dictionary, the objective value is equal to 15. Okay, and then I have x1, x2, x3, x4, and x5. What's the value of x1? 0. x2? 3. x4?
0.
3.
x3 is?
Oh, 3. No. 3.
What is x3?
3. Oh, x3. 7.
7.
S7.
Right, so again, you just look at, so for each of these, because everything here is a 0, then you just read off these values, right? So it's going to be that, and then x4 is what? 3, and x5 is? 0. Okay, so for all the non-basic variables, I have a 0, and all for the basic variables, I have just the b value. Okay, so that's where we are now. I sure hope to God this algebra is right. But what can we say about this? Do we get anything by incrementing x5? Do we get any improvement in the objective value? No, because I know that if any increment to x5 is going to decrease the objective function value. Okay, so that's for sure going to do some damage. What about x1? Will increasing x1 increase the objective value? Yes, because there's a plus sign there. Okay, so you can see the pattern here. So I know this is kind of like how the equivalent of finding an augmenting path. You're saying, okay, you look at the objective value, a function in your dictionary, you look at the coefficients. If any of these coefficients is positive, then we know that it's possible, conceivably, to increment the value of the objective function, provided what? So what limits the amount at which you can increase x1? What limits the increment to x1? Okay, so for instance, okay, let's say now that I want to increment x1. So I do the same analysis for each of these guys, and I see for each of these three equalities, and I see which of these constrains me the most. Which one constrains me the most?
X1. No.
All right, so first of all, let's agree that we're not going to change x5. Okay, now of course maybe there's some ways, and I don't know, you could imagine x5 could affect things. Let's say we just increase x1. We know that each of these x3, x4, x2 has to be bigger than or equal to 0.
Thank you.
X1 cannot be greater than 1. Why is that? Which inequality constrains it?
X4.
The x4, right? So this constraint here tells me that because x4 is bigger than or equal to 0, x1 cannot exceed 1. Right? So I have basically it's bigger than or equal to 0. So that if you do this, you get that if you just like you write minus 3x1 is going to be bigger than or equal to -3. So therefore x1 is less than or equal to 1. Okay? So, what does this tell me about the next objective function value? What's it going to be? 22. Okay, so if I were to write my next dictionary, which is going to be dictionary 3, I will have that z is equal to 22. And there's going to be something here which we might not have time to look at. Right, so I know, okay, so this was my tightest constraint. This one was the one that bounded me. I'm going to have a 22 here. Okay? And what will happen there? What will happen to x4? Okay, so I know that x4, when x1 goes up to 1, is going to drop down to 0. All right, so x4 will become a what kind of variable? X4 drops to 0, so it becomes a non-basic variable. And x1 goes up to 1, so it becomes a basic variable. So I've lost all confidence in the solution that I have posted here, but let me just write down what that final dictionary is. Okay, so you can of course do your own thing. I think the objective function at least is right. Maybe the constraints aren't, but this is what it looks like. So x1 will go on this side, and x4 will go on the other side. So what we'll have is that the dictionary will look like this. You'll have x3 equal to something, x1 equal to something, x2 equal to something. That part I think I'm okay with. And then over here, I will have something in terms of x4 and x5, which will look like this. And I'm not going to write the rest because, I kind of lost some trust in myself, but, Okay, so let's look at the objective function, and you can do the rest. Okay, so what can I say about the objective function? Well, first of all, the value is 22, right? I know that. Secondly, I know that, what, can I increase it? No, right, because if I were to increase, if I were to modify x4, x5, and the only way I can go is from 0 upward, I'm going to decrease the value of the objective function.
Yes.
Okay? So what I know for sure, at least based on what I've done so far, is that there is no way to increment this. So, in fact, I can conclude, so there's no positive coefficients. And I will conclude that the solution is optimal. Okay, so what happened is that I went from 0 all the way up to 22, moving along vertices of the feasible region until I got to a point where it wasn't possible to increment the objective value. And as we'll prove next time, that is indeed always going to be the optimal solution. All right, so I'm out of time, and I will check my math and get back to you on Friday.
Thank you.
在这个利益就可以找到最大值。